Alright, in this video, we see how simultaneous linear equations can be concisely expressed in terms of a matrix, and also how we can use matrix algebra to systematically solve simultaneous linear equations. Okay, let's start. So, we first define a convenient symbol called Kroneker's delta. Kronecker. So he's a mathematician, I think he's a German mathematician of 19th century, and Kronecker's delta. Delta is, of course, the Greek letter, and this is defined as this: delta ij, where I and j are integers, or actually it can be anything, but usually we use integers, is equal to 1 if I and j are equal, otherwise 0. So otherwise means when I is not equal to j. Okay, so that means, for example, delta 1 1, let's put comma to distinguish this from delta 11. Okay, it's not delta 11, but it's delta 1 1. This is equal to 1, but delta 1 2 is 0. And similarly, delta 13 14 is 0, and delta 13 is 1. Something like that. Easy. So using this Kronecker's delta, we define the identity matrix. Identity matrix. So identity matrix that is of n by size of n times n, it's a square matrix, is defined as this. Matrix is defined as this. So its elements are Kronecker's delta. So that means when I and j are equal, so that means it's on the diagonal, then the elements are 1, and otherwise, so if the elements are off diagonal, then they are 0. For example, in case of 1 1 matrix, it's just 1, right? Because it's just only one element, one element. And for 2 by 2 matrix, we have 1 0 0 1. So the diagonal elements are 1, and off diagonal elements are 0. And similarly, I3, we have 1 0 0 0 1 0 0 0 1. So again, the diagonal elements are 1, and off diagonal elements are 0. Okay. And if there is no fear of confusion, we just write identity matrix as just 1. So it's understood some size is assumed. Okay, so it can be 1 by 2 by 2, 100 by 100, or whatever. So in case we don't have to specify the dimensions, then we just write I. Of course, depending on the context, we can use any other symbol, but when we say the identity matrix, it's something like this. So all diagonals are 1, other elements are 0. The identity matrix is so called because it acts as the multiplicative identity of in matrix algebra. So that means this. So if we have a n by m matrix, then we have the following equality. In, so n by n identity matrix times x is equal to x. And also, x times m by m identity matrix is also equal to x. So the identity matrices, they act as multiplicative identities. So let's prove this. Okay, so the identity matrix, first consider this one. The n by n identity matrix is this, where I and j varies from 1 to 3 and so on up to n. Okay, so let's consider the ij element of this matrix. So in times x is a, so since this is n by n matrix, x is n by n matrix, and in is n by n matrix, the result is n by n matrix. So let's consider the ij element of this product. Then as by the definition of matrix product, matrix multiplication, we have k from 1 to n, and in, so this I and k, and x, this k and j, right? And by the definition of the identity matrix we have, so this is equal to delta ik, because it's the ik element of the identity matrix. Okay, now this term is equal to, okay, delta ik times xkj is equal to xkj, xkj, if this is 1. So in that case, I is equal to k, or equal to 0 otherwise. Right? So that means if I is not equal to k. This k varies from 1 to n. So there is only one k that is equal to I, right? It appears only once in this summation. So this summation here is equal to x, when k is equal to I, it is equal to this, so we have ij. So k is gone. So this means this is just ij element of the matrix X. So for any ij, we have this equal to this. Therefore, in x is equal to x. And we are done. In a similar manner, let's prove the second equality, this one. So xim, its ij element is this k from, now we are multiplying n by m matrix times m by m matrix. So the summation here is runs from 1 to m. 1 to m. And x, I, k, and im, k, j. But this thing is Kronecker delta. K and delta kj. Again, this is always equal to 0, except when k is equal to j. Okay? K runs from 1 to m, and one of them is equal to j, right? So this is equal to xi. So k, when k is equal to j, it has value. Otherwise, everything disappears. So we have this. So for any pair I and j, we have this equality. Therefore, the matrix product x times im is equal to x. And we are done. Okay, next we focus on square matrices. Okay, so let's see. Let's say x is an element of mn. So remember, this mn is the set of all n by n matrices, of n by n matrices. Okay, and let's say also y is such a matrix. Then if we have xy is equal to the identity matrix, okay, of course because both are n by n matrix, the result is should be n by n matrix. So if this holds, then we say y is an inverse matrix of x. So it's inverse. So it's a multiplicative inverse. And for a matrix X, if it has an inverse matrix, corresponding inverse matrix, then we say X is invertible. Okay, that means X is such a matrix for which its inverse can be found. Actually, an inverse matrix of X for any given matrix X, if it exists, then we can show that that inverse is actually unique. So uniqueness here means if there exist two matrices, so given X, if we have xy is equal to in, and also if there is another matrix Z that is that have xz times x times z is equal to the identity matrix. If this is the case, then we have y is equal to z. So in that sense, the inverse matrix is unique. So we say not an inverse, but the inverse of X. So because it's unique, we usually write the inverse of X as X inverse like this. So X is like X to the power of -1, but it's not power, but we denote like this to express is the inverse matrix of X. Okay, and we can also show that if X inverse is the inverse matrix of X, then by definition it should be equal like this. This should hold, but it also holds that X inverse times X is also the identity matrix. So X and its inverse, their multiplication commutes. So in general, matrix multiplication do not commute, but for a matrix and its inverse, they compute. Let's see simple examples. Consider 1 by 1 matrix. So this is very simple. So its inverse. So what's its inverse? So the inverse of this, let's call it C. Okay. So what's C inverse? If exists, then it should be, by the way, this C is a real number. If it exists, then it should be 1 over C, right? But this exists only when C is non-zero. Okay. And if this matrix happens to be the zero matrix, then the inverse doesn't exist. Does not exist. So there are matrices for which their inverses exist, but there are also matrices for which there are no inverses. Maybe this example is too trivial. Next, consider 2 by 2 matrix consisting of only 0. Okay, so this is 0 matrix, 2 by 2 0 matrix. For this one, there are no inverses. Okay, why? Because, so let's say, so in this case, this is 2 by 2, but for any 0 matrices of any dimensions, there are no inverses. So let's say if we multiply any matrix by 0 matrix, let's say A, B, C, D times 0, 0, 0, 0, what is the result? So if you try this, the result is 0, 0, 0, 0. Okay? Or maybe this was wrong. We should have multiply from the right. A, B, C, D. So let's say this is the inverse matrix of 0, 0, 0, 0. Then it should be equal to the identity matrix. But this cannot happen because the result is always 0 matrix, right? So for any matrix here, if we multiply the 0 matrix from the left, the result is the 0 matrix. It cannot be equal to the identity matrix. Therefore, no inverse exists. Next, consider a 2 by 2 matrix A, B, C, D, and we want to find the inverse matrix of this matrix. Okay, and we can actually prove that the inverse of this is actually this. That is D over delta and negative B over delta and negative C over delta and A over delta, where, close the bracket, where delta is AD minus BC. Okay, of course, this matrix is meaningful if this delta is not equal to 0. Otherwise, division by 0 happens, so it doesn't make sense. So as long as this holds, so this delta is non-zero, then we can show that this is the inverse of this matrix. Okay, this can be checked very easily. So what's the definition of the inverse? Just multiply these two. So A, B, C, D, and they are all divided by delta. So we can just put this 1 over delta outside, and put everything else, leave everything else inside, and A, and 1 over delta. So just multiply these two matrices, and AD and BC minus BC, and A minus AB and plus BA. So minus AB plus BA. So this will be 0. And CD and minus DC. So CD minus DC. So this will be 0. And minus CB and plus DA. Okay. Now, let's continue. So this is AD minus BC. So that's delta, and this is 0, and this is AD minus BC. So it's delta, 1 over delta. So this is, so delta divided by delta is 1, and 0, 0, and this is also 1. So this is the identity matrix. Therefore, this matrix is the inverse matrix of this matrix, A, B, C, D. So for 2 by 2 matrices, we can explicitly find the inverse as long as this delta AD minus BC is non-zero. So in other words, if this is equal to 0, then we cannot define the inverse matrix. Right? So that happens even when not all of A, B, C, D are 0. So even if they are even if the elements are non-zero, the inverse matrices may not exist. So that's a great difference from ordinary numbers, right? So in the case of real numbers, as long as the number is non-zero, we can always find its multiplicative inverse. But that's not the case for matrices. Even if a matrix is not zero matrix, its multiplicative inverse may not exist. We give a name to this mysterious quantity. So for 2 by 2 matrix A, B, C, D, for this matrix, the quantity defined as A times, so 1, 1 element times 2, 2 element minus 1, 2 element times 2, 1 element. This is called the determinant. Determinant of this matrix. And if we denote this matrix as X, then determinant of X is maybe usually denoted as det X, or sometimes bar X bar. So it's like the absolute value of X, but in this case, it's not absolute value, but it's determinant. Of course, if all the elements are real numbers, then the determinants are also real numbers. Okay, so don't confuse this with absolute value of some real number, but it's something like absolute value of matrix, but it's not absolute value. It's not magnitude. So this can be either positive or negative or zero. Okay, so don't get confused. And we are going to define the determinant for more general matrices, like n by n matrices. But before that, let's see the connection between simultaneous linear equations and matrices and determinants. So consider the following equations: ax plus by equal to p, and cx plus dy equal to q. So this is a set of simultaneous linear equations of x and y. So here a, b, c, d, and p and q are given real numbers, and x and y are variables to be determined. So how do we solve this equation? Of course, you should know how to solve these equations, but here we show application of matrices. Okay, so these equations can be concisely expressed in terms of a matrix and vectors. Okay, so first let's define a matrix A that is made of these coefficients on the left hand side. So A, B, C, D. And that vector x be the column vector made of the variables x and y. And also another column vector, let's call it p, made of the values on the right hand side, p and q. Okay. If we use this matrix and these vectors, these equations can be concisely expressed as a x equal to p. Why is that so? So let's see this one more explicitly. So a, b, c, d times x and y. So let's calculate this one. So this is 2 by 2 matrix, and this is 2 by 1 matrix, so they can be multiplied, right? So a times x plus b times y, and c times x plus d times y. So that is the left-hand side of these equations, right? And of course, this right-hand side p is just this column vector. So if this is equal to p and q, and if two vectors are equal, then each corresponding elements are equal. So that means ax plus by is equal to p, and cx plus dy is equal to q. So that is precisely this set of equations. Now, suppose the determinant of this matrix A is non-zero. Then we can find the inverse matrix of A. If the determinant of A is non-zero, then A inverse exists. Okay, so let's multiply both sides of this equation by A inverse from the left. So if this holds, then we have A inverse AX, A inverse P. Right? And for this one, since matrix multiplication is associative, this is equal to A inverse times A times X. Okay. But since we are multiplying A and its inverse, this is equal to the identity matrix. Right? This is equal to identity matrix. But identity matrix times a matrix is equal to this matrix. So I times X is just equal to X. So if we can calculate the inverse matrix, so So inverse matrix times this vector is another vector. So in this way, we can find the values of x and y. Previously, we have shown that this A inverse when A is A, B, C, D is given by, what was it? D over delta, negative B over delta, negative C over delta, and A over delta, and PQ. And of course here, delta is the determinant, AD minus BC. And if we just calculate this, so dp minus bq over delta and negative cp plus aq over delta. So this is equal to x and this is equal to y. So that's the solution. Let's compare this result with the result you obtain by directly solving these equations. Let's see a more concrete example. Okay, let's see. So consider these equations. 2x plus y equal to 1 and 3x minus y equal to 0. Okay, so these equations can be expressed as matrix equation. So 2, 1, 3, negative 1, x, y equal to 1, 0. And for this matrix, the determinant is this times this minus this times this. So 2, negative 1 minus 1 times 3, that is negative 5. And the inverse matrix should be, so negative 1 over negative 5, and what was it? Negative 1 minus 3, 2. So this should be the inverse matrix of this matrix. So if we multiply this matrix to this vector from the left, then we should have the result. 1 over 5, negative 1, negative 1, negative 3, 2, and 1 and 0. So that is negative 1, 0, and negative 3 and 0. So that is 1 over 5 and 3 over 5. So x is 1 over 5 and y is 3 over 5. Although we have worked only with 2 by 2 matrices so far, the same procedure can be applied to matrices of any size, so any n by n matrices. Of course, we have to define the determinant for that case, and also we need to find out how to find the inverse matrix using that determinant and other procedures. But the principle is the same. So once you understand this principle, you can solve, at least in principle, solve any simultaneous linear equations as long as there are solutions. And of course, you can also determine the case where there are no solutions because the inverse matrix may not exist. Okay, that's all for this video, and see you later.